Okay, so we should see a bright flashing red light in the upper left-hand corner of our Zoom windows, which indicates recording. And I will hand over the floor to the group and let them share with us their microbioreactor design.
All right, thanks, Matt. I'll go ahead and share my screen. So hi, everyone, and welcome to our final presentation. We are CultureBot, consisting of Jack Adams, Alexander Knoll, Buck Daly, who unfortunately couldn't be with us, myself, Adam Edwards, Uday Katravalapalli, Josh Orteza, Jake Sadowski, and Serene Spaklo. Jake, you're muted.
Sorry, thank you. The CultureBot is a versatile microbioreactor with full automation. We aim to provide a system that can accommodate a wide range of labware, including well plates and conical tubes, as well as a large range of controllable culture conditions. The CultureBot is designed to control the fluid addition and subtraction of well plates and test tubes, handling of well plates and test tubes, incubate cells at a wide variety of temperatures with 3 distinct shaking patterns in individually controlled environments, and automated ODFI measurements. The manual setup requires the user to preload the well plates and test tubes with cell cultures, as well as adding or removing disposable tips and filling reservoirs with the proper chemicals or reagents required for experimentation. Once the CultureBot is physically set up and ready for testing, the user will set the desired controls via the user interface located on the outside of the microbioreactor. These controls include setting the well plate or conical tube size, the number of occupied incubators, incubator temperature, gas concentrations, photobioreactor LEDs, number of occupied reagent reservoirs, assignment of particular reagents to their specified wells or tubes, and the duration of the experiment. Once the user has inputted all of the controls, the CultureBot will then complete the entire process without the need for any more human intervention. The total time for one cycle is just about 7 minutes. This was calculated by finding the time it takes for a well plate or test tube to move between subsystems, in addition to the time that it takes to process each well plate or test tube at each subsystem. The overall weight of the structure is about 220 pounds, which is about 1/3 of the maximum weight requested by the customer. We wanted to make our microbioreactor as versatile as possible, so we designed it to support up to 3 independent experiments at one time.
With the exception of the gas injection subsystem, the structure houses each of the remaining subsystems in CultureBot. On its own, the structure weighs around 61 pounds after it's fully assembled. It's made of 16 gauge 1010 low carbon steel. The bottom plate is 3/16 inch aluminum sheet metal, made to be slightly thicker to withstand the weight of the internal components and to mitigate vibration from the shaker system. We added rubberized feet underneath the bottom plate to ensure there's enough friction between the bottom of the structure and the table it's sit on. The back plate is made of 1/16 inch aluminum sheet metal and has rectangular cutouts to accommodate the tubes that connect the gas manifold to the climate control units. Transparent polycarbonate panels are fastened to the sheet metal frame using push rivets. There are 2 hinge doors placed on both sides of the structure to access it from either end. And the control box houses all of the motor controllers, a Raspberry Pi unit, and any other electrical components. We also added an LCD display mounted on the outside of the structure to allow the user to input desired controls on the culture conditions. And if you go to the next slide. Oh, that is the wrong slide. Go back, sorry. 1.5 inch diameter stop button was included to halt all operations in case of an emergency. And since the proof of concept is established for the subsystem, we decided that it has a technology readiness level.
Our handling system is a combination of lead screw gantry system and a grabber that can lift up the well plates and transport them to different parts of the bioreactor. We calculated how long it would take the lead screw to move the well plate from the liquid handling into the shaker, out of the shaker, and dropping off into the ODFI, which we found to be 95 seconds. The NEMA 17 motor rotates the lead screw, which converts rotary motion into linear motion. This works in the X, Y, and Z axis. We use the sheet metal for the grabber, and the support blocks are made up of nylon 666. The linear actuator extends and retracts to pick up the well plates from underneath. When we designed this system, we made sure the Z-axis of the gantry system did not interfere with the sheet metal grabber. And the sheet metal grabber is attached to the linear actuators with L brackets. Next slide. The second analysis we did was a beam deflection analysis. This beam was fixed on both ends. We wanted to find if the bending had a negative impact on the performance of the handling. We did an analysis on the bottom 303 stainless steel rod. The rod is fixed at both points, so using the deflection equation, we found how much it deflects. We found the deflection to be 0.21 millimeters. Next slide.
So our liquid transfer subsystem is designed to dispense and aspirate fluid media into and out of well plates and conical tubes of a range of sizes. The overall subsystem is designed to be a station with a couple of key components, and I'll walk you through those components in the order they would be used by the system. So first is the well plate table, which is to elevate the well plates at the bottom of the structure in order to be picked up by the hand system. The well plates or the test tube racks are respectively on either the well plate table or on L brackets that elevate the test tube rack from the bottom of the structure. Once the well plates tubes are in place, the lids are removed from the well plates using the gripper and placed on a separate table, which if you go to the next slide, hidden between the liquid transfer system and the units. And so this picture gives a better view. And from there, the transfer process starts. Next slide, please. Prior to the start of the experiment, the desired agents are manually loaded into the fluid reservoirs, which is a 125 milliliter Nalgene bottle into which a tube is inserted. This tube is fed into a modular valve manifold, which dispenses a particular fluid by opening and closing the corresponding valve. The fluid is then transferred to the pipetting unit, it's dispensed out of a disposable pipette tip using a peristaltic pump. Next slide, please. You can see that pipetting unit clearly on this slide. This unit moves on an XYZ lead screw system powered by NEMA 7 motors in order to achieve precise motion and position itself above the center of each well tube. Mounting blocks on this unit were 3D printed using nylon 666 to reduce the deflection cost of weight placed on the support shafts. In order to meet the volume requirements set by the customer needs and to prevent cross-contamination, we decided to use a peristaltic pump connected to a pipette tip to force fluid through the tube using positive display. The pump is indexed through partial revolutions of the motor to accurately dispense small fluid at a time. The OS pump we chose can achieve a flow rate of 100 microliters per second, and we calculated an overall time for a 384 well plate to be just over 2 minutes. The pipette tip is a universal disposable tip that's going to be press fitted onto the pipette body, and when it needs to be replaced, it's inserted into a hole in the waste container, and the unit is moved left to right to overcome that interference fit. Next slide, please. An all-purpose waste container is placed on the side of the liquid transfer station. It contains 3 compartments, one to hold new pipette tips on a rack, one that contains solid waste, which is disposed pipette tips, and one that sequesters the neutralized fluid. So when the system needs to aspirate fluid out of a well or the manifold would open the valve connected to the waste container and pull the waste fluid into the bin. Then to cleanse the system, the pipette moves over to the waste container. 2 Nalgene bottles are reloaded with bleach in a PBS solution that flushes out the system and neutralizes the tubes. The waste container has a maximum capacity of 100 or 1,000 microliters. The entire tubing system was calculated to have a volume of 3.14 milliliters. So that waste container can hold the entire volume of fluid being flushed out several times. And because the proof of concept was established by the following analyses that were conducted, decided the subsystem has technology readiness level 3. Next slide, please. Since the long lead screw on the x-axis needs to support the weight of the pipette unit, we calculated the maximum vertical deflection of that support shaft using analysis done on the handling subsystem, and we found it to be 0.61 millimeters. Next slide. The more critical deflection analysis that we performed was the angular deflection pipette tip. Lead screw in the y-axis was acting essentially as a cantilever beam. We found that the maximum slope of the lead screw, if the pipette was at the farthest distance in the y direction, that deflection would be 0.035 degrees. Since the diameter of the smallest well to be filled was 3.65 millimeters, this deflection was essentially negligible and caused the pipette to interfere with the side of the well. Next slide. The Reynolds number was then calculated to make sure that the flow out of the pipette tip diameter and would not create aerosols. We assumed that the fluid dispensed had the same viscosity of water, which we consider to be the worst scenario because it has the low viscosity, and the Reynolds number was found to be 939, which is significantly lower than the 23,000 threshold for turbulent flow. We also did a calculation to determine precision achieved by the pipette tip based on minimum rotational speed of 0.1 rotations per minute or 0.6 degrees per second. We're able to find the minimum volume dispensed, which is 0.007 microliters, which meets the customer need of a 0.01 liters.
Our climate control units are separated into 3 individual modules, where each is heated or cooled using Peltier plates to achieve the desired temperature range of 4 to 70 degrees Celsius. The casing is separated into 2 sections, one internal and one external. One side of each of the Peltier plates is in the internal and external sections. The internal section on the right side of the diagram has fans to circulate the air within the climate control module, which is not pictured here yet, but contains the well plates or conical tubes and a shaker assembly. The external section has heat sinks contacting the Peltier plates to dissipate heat and fans to move air across the heatsink fins. The external section sticks out of the overall bioreactor structure so that heat isn't dissipated within the structure and getting trapped inside. When the unit is in operation, the internal side of the Peltier plates is powered to either heat up or cool down, depending on what you want the temperature inside of the module to be. So let's say you want the temperature inside to be 4 degrees Celsius. That side of the Peltier plate cools down, and the opposite side in the external section heats up, and the heat sinks dissipate the heat generated to maintain the temperature differential between the 2 sides of the plate. If you wanted to heat up the cell cultures instead, switching the direction of the current supplied to the Peltier plates switches the hot and cold sides to then heat up the inside of the module. The plates are controlled using closed loop feedback with a temperature sensor inside of the module that has an accuracy of 0.5 degrees Celsius, meeting our customer need. The climate control system received a technology readiness rating of 3 because the concept has been analytically demonstrated with calculations involving the heat convection rate of the heat sinks and further heat transfer calculations. Next slide, please. So we calculated the amount of heat that can be dissipated by the heat sinks to ensure that they're able to maintain the maximum temperature differential of 66 degrees Celsius from the Peltier plates. The heat sinks also dissipate the heat generated by the operation of the plates, which comes to a total of 157 watts. So in total, they can dissipate about 171 watts each. Next slide, please. So this is the climate control module box. The modules each contain a shaker assembly, well plate or tube rack holder, a temperature control unit, polyethylene foam insulation to prevent temperature interference between the 3 separate units, and a servo-controlled door for automated opening and closing. There are also 4 LED lights located on the inside of the door for any cell cultures that are able to photosynthesize. To seal the internal environment of the box, there are rubber gaskets located around the rim of the openings of the door and where the temperature control unit is inserted into the module box. And finally, the outer part of the module is made of steel sheet metal for a sturdy structure. Next slide.
All right, continuing our climate control analysis, there were 2 customer needs that we wanted to address in particular. Need 20, which is maintaining a constant temperature in a range from 4 to 70 degrees Celsius, and need 24, which is reaching a set point temperature in less than 15 minutes. To be able to determine this, we used an electric analog of our incubator that includes the air inside the incubator, the polyethylene foam lining, the 1010 sheet steel wall, and the ambient air outside of the incubator. We assumed the highest set point temperature of 70 degrees inside and ambient air on the outside. We found the heat flux using the equation in the top right, which we determined was 204 watts per meter squared. We accounted for the area of the incubator and multiplied that by the heat flux to find an energy balance where we compared our cooling power to the amount of energy leaving. 96 was greater than 45, so we determined that we are able to maintain that steady temperature. Next slide, please. Knowing that we are able to maintain the temperature is just not enough, though. Customer need 24 prescribes a 15-minute period to reach that desired set point temperature. So we use the heat capacitance equation, which when rearranged is Q is equal to C delta T. We maintain that same temperature differential of 70 to 25, and the heat capacitance accounts for all of the mass inside of the incubator, which includes the well plate, the shaker subsystem, and the air inside. When multiplying the two values together, we found that we required at least 37 kilojoules. And when we divide that by our input power, we find that it takes around 7 minutes to reach the desired set point temperature. In addition to this, we noted that our incubators were placed very close to each other, about an inch apart. So we wanted to see if the heat flux leaving one incubator would interfere with the temperature of another incubator. To do this, we go back to our electric analog using the heat flux from the incubator at 70 degrees Celsius. We calculated the temperature inside of the incubator adjacent to it and found that it is indeed negligible. Next slide.
Okay, and so continuing off of that, we have, like we discussed, 3 distinct shaker patterns. And this follows through on our hedgehog concept of us wanting to be versatile with our design. And so each of these individual shakers is housed within the climate control unit that you just saw before. We offer a linear, orbital, and double orbital shaking pattern. These can all 3 house either a well plate or a test tube rack, which we will be offering with our product that would be 3D printed in order to hold those test tubes. Beginning with the linear motion shaker, we have a NEMA 17 stepper motor, which is going to be driving the system with a max operating RPM of 750. This is going to be housed inside of a nylon 666 motor housing, which we'll also use to support the cam here that's depicted that operates the rotation. This cam functions similar to how a beard trimmer works, where they have the cam spinning and then it's set in between 2 rectangular extrusions, which then move the slide back and forth as the cam rotates itself. This is also supported by these bearing carriage sleeves, which will allow us fairly smooth motion as we have the weight on top of this oscillating back and forth. This offset, the offset on this cam is around 0.4375 inches. So we'll get a linear travel of just about that same amount. For the orbital shaker, we have a similar setup with the same NEMA motor, same 3D printed housing. However, now we've got 5 offset orbital hubs, and the center hub will be driven by the motor, and the center hub is going to be made out of a I believe we chose a 1020 steel, a 1020 cold rolled steel, and just for some added strength. And this will be driven directly by the motor, but all of the weight of the system will be supported by the bearings and the housing, so that there's no additional stress on that motor shaft. These additional supports will also be press fit into these bearings in order to alleviate any stress that would be put on the main driving hub. In order to verify this, we wanted to look into a fatigue analysis because it was recommended to us by some of our peers as well as professors. But we thought longer on it after realizing that the stress that is being seen here is not going to be an oscillatory stress. And so we couldn't really perform a fatigue analysis due to the fact that as all of this system is rotating, the force is not alternating along the shaft. It's moving with the shaft the entire time. So we approximated this to a statics analysis in order to determine if the loading conditions or the weight was going to break the hub. And so we did a combined loading analysis in SolidWorks where we fixed where the motor shaft would be acting upon the internal face of this component. We combined the a 1 pound normal force, which is 2 times larger than what we would potentially see based on the components that we have that would be loaded onto this. And then I found the centrifugal force based on the max rotating RPM of the motor, which was 750 degrees, and the motor's specified max starting torque of 0.36 Newton meters. With these conditions applied, we saw a max deflection of 0.002 millimeters and with a factor of safety of 6. So we felt that that was sufficient. And for the double orbital shaker, we combined some literature on double orbital shaking patterns from around the early 1900s, where if you have two gears that are rotating with respect to each other in opposite directions and their connection points are offset by 45 degrees from horizontal, you can achieve a figure-8 motion through use of a linkage with a specified length with respect to the positioning of the original gears. And so I performed that here in order to get this small figure-8. We spaced the gears out further apart and made the linkages slightly longer in order to decrease the size of the orbit itself. And this also has a very similar setup with the NEMA 17 motor, bearings, carriage sleeves, the well plate support, and nylon 666 support housing. We chose nylon 666 because it's a higher, I'm sorry, let me rephrase. We chose this material because a certain company sells it in spools, and it has a higher thermal resistance than some of the normal 3D printing materials that you would usually see. And this specific material from the company, it was 3D X-Tech, I believe, boasted about their durability and their thermal resistance and lifetime. So we chose to use this material because this housing and all of these parts are going to be inside of the climate control unit, experiencing temperatures of up to 70 degrees Celsius or as low as 4 degrees. So we wanted to have a wide variety available to us in terms of materials and to ensure that it's not going to melt or warp over time.
For our ODFI system, we decided to use an entirely closed system made from aluminum sheet metal to prevent any light from entering or altering the measurements. Our overall handling system that was described earlier is designed to carry the well plates or test tube racks over to the ODFI system all autonomously. Before the well plate even reaches the ODFI system, an automated door driven by a servo motor will open, allowing the specimens to be inputted into the ODFI well plate holder. The well plate holder is hollowed out on the bottom to allow for the light to hit the cells with minimal interference and or refraction, which could affect the metabolic data readings. It was also designed with the entire handling system in mind. A close-up look shows how we intend to insert and remove the well plates or test tube rack to and from the ODFI system. There is enough clearance on the sides and on the bottom of the well plate holder to allow the gripping mechanisms to grab the well plates and test tube racks. We opted to use a lead screw driven gantry system identical to the one used for our main handling system, except with the motion only in the X and Y axis, and slightly shorter lead screws and shafts to accommodate the size of the ODFI system. The gantry system has a precision accuracy of plus or minus 0.0003125 inches, meaning it can take readings on each individual well without taking readings on the wrong well. This gantry system will be used to position the individual wells of a well plate as well as individual test tubes in the test tube rack over the objective lenses. The lead screw system can move the well plate at 0.78 inches per second at the NEMA 17's maximum rotation speed of 750 RPMs. This means that a 384 well plate can be processed in just over 3 minutes if an imaging time of 250 milliseconds is used. The objective lenses are brought within 1 millimeter of the bottom of the well plate holder to ensure the most accurate measurements possible. Similar to what you may see on a confocal imaging microscope, the objective lenses are positioned on a rotating carriage to allow for a variety of different lenses depending on the type of measurements the user would like to take. The rotating carriage is attached to a high load bearing rotary table and is rotated using a NEMA 17 stepper motor for precision accuracy. Directly underneath the objective lenses is a 30 millimeter dichroic beam splitter, otherwise known as a 50-50 lens, to allow for the light to be split to the proper wavelength to excite the cells at the fluorophores' desired wavelength. The light source for the ODFI measurements is an OTS fiber optics illuminator with PWM controlled intensity, which allows for even more autonomy. The fiber optics cable is then ran to an OTS motorized filter wheel, which allows for up to 6 filters of various wavelengths. These filters can be cycled through autonomously at any point in time during the experiment, depending on the wavelength needed to excite the cell's fluorophore. The motorized filter wheel is also compatible with our 30mm cage system. The 30mm beam splitter is attached to this OTS cage system, which can accommodate a wide range of different tube lenses, apertures, and other various optic mounts that may be needed for cell imaging. The setup seen in the picture depicts a very basic cage system to allow for simple OD and FI measurements. However, the bottom of the ODFI system has plenty of empty space to accommodate additions to the cage system if so warranted by the user, which would allow for more complex metabolic data measurements. Essentially, the excitation light will travel from the LED source, through a filter, through the beam splitter, up through the objective lens, and to the bottom of the well plate, where it will excite the cell's fluorophores. This will create an emission caused by the fluorophore that will travel back down through the objective lens, through the beam splitter, through a tube lens, through an aperture, and into a photoelectric sensor where the data will be transcribed and recorded. The fluorescence intensity in our microplate reader is detected with a photomultiplier tube, otherwise known as a PMT. It multiplies the signal using a photoelectric effect and converts the light into an electric signal. For fluorescence intensity measurements in our microplate reader, a low noise blue-green PMT is used due to sensitivity in the range between 185 and 870 nanometers, which includes every wavelength of light in the visible light spectrum that could be necessary for OD and FI measurements. Next slide. Taking a closer look at some of the individual components of the ODFI system, you can see the open design on the bottom of the well plate holder, which allows for the system to image cells with minimal interference or refraction. The well plate holder was also specifically designed to accommodate the grippers on our handling mechanism by adding a small gap both underneath and beside the well plate. Next slide. Here we can see a close-up of some more individual components, including the OTS 30mm cage system and cage system compatible beam splitter, as well as a more detailed look at how the rotating objective lens carriage operates. We rated this concept as a technology readiness rating of 2, since the only calculations done for the system were processing time and accuracy. It is a feasible design, however, more analytical and experimental data would need to be gathered for it to be considered a technology readiness rating of 3.
All right, for the gas injection system that we have designed, we included a 6mm outer diameter flexible polyurethane tubing, as well as various adapters to different gas regulators for compatibility with various laboratory setups. From these gas hookups, the required gas flows through an array of mass flow meters, which then connect to a series of solenoid valves, and these interface together to allow the user to input a desired volume of each gas to be injected into the incubator. And the valves close once the target has been attained. From there, these 5 gases connected to a 5 inlet gas manifold, which then connects to a 3 outlet gas manifold. And these, the outlet manifolds connect to 3 explosion-proof solenoid valves to allow the user to control what combination of gases goes to which incubator. This is also connected to check valves to prevent backflow. Additionally, we have a gas removal system, including 3 explosion-proof solenoid valves, a 3 gas outlet manifold, and a vacuum pump, which requires an 8mm inner diameter tube. The vacuum pump is placed inside of the lab's fume hood and manually turned on by the user if gas removal is desired. And it also creates a partial vacuum in the incubators, promoting flow of the gases via pressure differential from the gas source to the incubators. The gas lines can also be flushed simply by manually removing one of the plugs attached to either the 5 or the 3 outlet manifolds in the gas injection system, allowing the vacuum pump to pull ambient air to flow through and flush out gases. Next slide, please. Performing a pressure loss calculation of the system, it was found that due to major and minor losses throughout a given fluid path, and assuming the gas is made up of 100% carbon dioxide, the worst case scenario due to its high density, the pressure drop is approximately 1.3 psi. The friction factor was extracted from a Moody chart assuming a smooth tube surface, and after calculating the Reynolds number, it was confirmed that the flow is indeed turbulent. And this may vary if the lab configuration demands a longer or shorter tube to connect to gas injection apparatuses, but the calculation assumes a total path length of 0.508 meters. And due to specifications set by the flow meters used, the system operates at a maximum volumetric flow rate of 20 liters per minute. As long as there are pressure difference of at least 1.3 psi between the gas inlet and an incubator, the design will be free from adverse pressure gradients within the fluid path. Next slide.
We calculated the cost of a bioreactor. The most expensive in terms of raw material was the structure because of all the sheet metal. The most expensive in OTS was the gas injection system. Our assembly labor was above average of what most people had because of the number of parts we have to put together, but we are still under the $10,000 budget. Next slide.
So why CultureBot? So overall, CultureBot offers a comprehensive package that can integrate cell incubation and sample interrogation through shaking by placing our shakers inside climate control units. It offers periodic metabolic data measurements through our ODFI system, environmental control, as well as liquid handling capabilities, and it combines all into a single autonomous self-regulating unit. Since it's fully autonomous and it requires no user intervention during an experiment, it makes it as hands-on experience as possible. With a wide range of input variables, CultureBot accommodates a variety of experimental setups. Compared to what's on the market today, our product offers a lower price point while performing functions in one all-encompassing device. Next slide. And we just want to thank Dr. Traum, all the teaching assistants, faculty, and our corporate sponsors for your support and for coming out to listen to our presentation today. So at this point, we'd like to open up the floor for any questions that you guys might have.
Okay, great.
Hello. I've got a couple of questions here. Dr. Traum, if I may.
Sure, yeah.
Could you go back to the pump slides? I'm curious what kind of vacuum pump you're using.
So that vacuum pump is an oil-free laboratory vacuum pump.
Okay. That's what I thought based on the drawing. Okay. So if it's oiled, how are you going to prevent the oil from diffusing?
Oh, it's not. I'm sorry. It's oil-free. There's no oil in there.
Oh, oil-free. Okay. All right. Perfect. Could you go back to I think it was one of the climate control slides, I think earlier on in the presentation. Let's see. Yes. I think this is what I was trying to think of. So what I was interested here, so did you guys consider, did you use foam as an insulator?
Yes, it's polyethylene vinyl, like closed up.
Okay. Did you guys calculate the Rayleigh number? I didn't see that.
We have not for the climate control.
Okay. Because I mean, I'm just looking at this sort of logically. Wouldn't air be a better form of circulation than foam?
I don't think I understand. Circulation, you said?
So the way I think about this is that you could have calculated the Rayleigh number in the void space to determine if the air would begin circulating, right? So if circulation occurs, foam is okay to use. If not, air is better than foam. Does that make sense?
Yeah, we didn't do that calculation yet, but we will for the final design report.
Okay. Awesome. That's it for me.
While we're talking about the climate control system, can you flip back one or two slides, or one more? Okay, so what I'm looking at here on top, you've got fans blowing over heat sinks, right? So you've got air flowing past heat sinks. You're dumping thermal energy into or out of the air, and it's going elsewhere. And then you seem like you have fans mounted right on the surface of the Peltier plates. Is that correct?
There is a space between the Peltier plates and the
Oh, there
fan.
is. Okay. Okay. So you've got air flowing through that channel there then.
Yes, we did another calculation to ensure that the air take matched the outtake from the fans.
Okay, good. Yeah, yeah, I was wondering where the air went. Okay, let's see. You showed 3 different shaker arrangements for linear orbital and double orbital patterns. Does that require a user to swap parts out?
When you say swap parts out, are you talking about like if we wanted to do one pattern or the other?
Yeah, I mean, do they have to do some setup of the machine and you know, install a different mechanism to achieve a different shaking pattern?
No. So maybe I can show you in the main assembly picture here. So each shake, there's 3 climate control compartments here. Each one of these is designated to a pattern. So one is orbital, one
okay.
is double orbital, one's linear.
So they are specific to a pattern, but you've got all 3 in the box.
Correct. Yeah.
So if a user wants to do an experiment and says, hey, I need you know, 3 well plates and I want them all to do an orbital shaking pattern, then they need
in
3
that case, they would need to.
CultureBots?
Well, we could probably market it or sell it as if you want to buy the individual shaking unit, then they're swappable. The only thing that would need to change is if there's a foam insert on the bottom as part of the installation that has a cutout specified for one of each size. So you would need to just replace the foam insert, and then you could probably buy our shaking unit and just swap them out modularly if you wanted that specifically.
Okay, I'll say that's cumbersome for a user, and I would imagine that, you know, if I want to use 3 different climate control units, probably I would want to keep the same shaking pattern for each culture that I've gotten there. And on the subject, I think you'd mentioned that you didn't see any reversing loads in your shaking system.
We figured we would talk about this with you guys as well. We sat on it for a while trying to think about it and look at what stresses would be occurring, and we had convinced ourselves that there wasn't going to be a reversible load because of the way everything is mounted and sitting, but we figured you guys might know if that's true or not. We had attempted to convince ourselves of that though.
So I'm not a mechanisms guy, and maybe somebody who's on the line is and can speak to this better than I can. I think maybe I'm convinced that that's the case for specifically this orbital pattern shaking, but for anything else, I'm pretty sure you would have reversing loads. You know, if you flip back to like the linear shaking right here, I mean you've got loads on your pin here that are maximum when it's sort of, you know, at 90 degrees and 0 when it's at 0 degrees, right? So you're definitely going, you maybe aren't going a fully reversing, but you're going, you know, from 0 to 1, right? So that's a 50% reversing load there.
Right. Okay. Yeah, and that makes sense now that you said it. I think part of it is the tired brain not working properly.
If we were to do it, we would have to include the inertial force of the well plate holder, which would probably be the reversing force, because we were trying to find it, and it's hard to find it on an offset bearing. I spoke with some of my other colleagues, and they were saying that we could use the drive torque along with the mean stress, which would just be the weight of the well plate acting on it. But as far as a reversing stress, we figured it would be the moment of inertia caused by it, but I guess that was a little bit difficult for us to get in the time being that we started considering this. So it's definitely something we're going to look more into for the FDR for our final design report. But as of now, we don't have a true fatigue life rating for that.
Okay, what's the material that that your I guess your cam and your follower are made out of here?
So the follower is the 3D printed nylon 666. The cam would be would probably need to be a CNC part. We wanted to look into 3D printing the cam, but there's no SN curve that we could find in order to perform the fatigue analysis. And it seems like fatigue analysis on plastic parts is still up and coming in industry right now, and there's still a lot of research being done into it. So,
yeah, that's going to be one of those situations where you got to test to find your own curve, most likely.
Exactly. So we changed it to steel instead, and we just figured we'll do it CNC this one part, because we overall that the only CNC work that we have would have been these cams. So that's kind of what we changed it to in order to actually, because now with it being steel, we can actually perform that fatigue analysis. We have data to back that, and we know what we can find an answer. So.
Okay, and one more thing while we're looking at shakers, do you have any concerns with resonance in your system with any of the the frequency that you're shaking at versus any of the natural frequencies of the rest of your system?
So we did have concerns, because at the very first time we went through the iteration of this design, we had talked to Dr. Traum, and he had mentioned that to us. We looked into, I don't have a picture of the bottom, but I can show this to kind of explain it. So our resonance, where we would be most concerned, would either be on this bottom plate here or the sheet metal structure of the climate control unit itself. We had started to perform some calculations in order to determine the equation of motion for us to even find out if we were going to be close to any resonance values. We might have just been overthinking it, but we were unsure about whether or not we would actually have an issue. So what we did to mitigate this is we originally had this plate on the bottom was a 16th inch sheet. We thickened it to a 3/16 inch plate so that it's a lot more stiff. And we evaluated the deflection of this plate under its own weight. It was less than 0.5 millimeter. It was, I can't remember the exact number, so I don't want to exactly say, but it was really small. And then on top of that, we also placed the rubberized feet that Serene discussed. We placed 3 of those directly under the center of where the motor would sit within the climate control unit. Back here. So as you can kind of see it here, there's going to be a center point in which the motor would sit on the steel sheet metal structure, because we would have a cutout in the foam for the motor to sit, and so we could mount the whole thing through to keep it still. So we added a foot, one of those rubberized feet, directly underneath the structure where this motor would sit, in order to try and compensate for that in case there would be resonance. But we could not, we kind of got stumped because half of us have not even taken that class yet. So we're kind of,
oh man, I never even took that class.
Yeah, we're kind of swimming in the deep end there. But we definitely wanted to think about it and wanted to make sure that it was not going to cause us an issue, but we weren't sure how to get to that final answer. So we did some other things to ameliorate that situation.
Okay.
Adam, if I could jump in here real quick, just one more question, because we're on this slide. I was kind of curious, did you guys learn about correction for corners and heat transfer? Do you guys remember? Did you learn about that?
I don't remember personally learning about that.
Yeah, I don't think so.
I'm not sure we covered that.
It should be in our curriculum. If it's not, I need to go look at the syllabi. But, you know, there should be additional conduction at the corners that might not be accounted in this model. I don't know. Dr. Traum or Dr. Brooks might know more than I. So I don't know if they want to jump in, but just looking at this, I would think there would be more conduction.
Oh, sorry. I just wanted to say from what I recall from when I took heat transfer, however long ago that was, I guess last semester, there is a method of determining the heat transfer and the heat flux through corners. So that would probably have to be a calculation that we would have to consider for the FDR.
Okay, awesome.
Mm-hmm.
Dr. Traum, do you want to chime in?
Well, I was just going to say as a follow-up question, recognizing that you haven't done the corner analysis, but just qualitatively, can you give us a sense of whether the 1D analysis that you did do is a upper bound or a lower bound relative to additional heat transfer at the corners?
Using the accounting for the largest area of a side, we assume that all sides were that largest area, and then using that highest temperature differential of 70 to an ambient air, we could say that we accounted for an upper bound.
But so hang on, tell me again, because there's a lot more going on there than I expected. So you used
We used
largest,
the highest set point temperature of 70 degrees.
Yeah, that's okay.
We
Something
also
about area though.
we assumed we found the area of each of the sides, and we took the side with the largest area, and we assumed that all sides were that area in our calculation.
Oh boy. Okay. So the thing that the thing you're showing here is basically a monolithic rectangle, but it sounds like what you've actually modeled is a cube.
Right.
Okay, so you've given it effectively. Oh, okay. Now I got to think through this. You've given it more heat transfer area than it in your model, more heat transfer area than it actually would have in real life.
Yes.
Okay. So that makes the question of corners actually even more interesting, but also more complex, because so anytime you restrict, oh, hang on, that's my alarm going off telling me that you're at your 45 minutes. So anytime you restrict a path of heat transfer, you're basically forcing your model into a lower bound. So by using the 1D model that you've got here, that would normally be a lower bound, but you're now mixing two different geometries, and the geometry that you selected was one that would give you an upper bound. So does that make sense? So you guys are like, so what one assumption is sort of the lower bound, and the other one's an upper bound, and now you're mixing them together. So I think the best we could say is that you've sort of got an estimate, but it's not a bounding estimate either on the high end or the low end for heat transfer. So okay. Huh. You guys didn't, you did do corners though, right? That's in the curriculum somewhere, like in the heat transfer course.
I believe I remember doing corners and flat walls, corners, and different angles.
Okay, yeah,
I don't
okay.
remember doing corners.
I don't know if this is
We all had different professors.
specific, but
Oh
Yeah.
no.
And
Well,
also about half our team, more than half our team is in heat transfer right now. So
But it's the last week of the semester.
it is the last week of the semester. That's fair.
And corners is conduction, so you should have done it probably in the first 5 weeks. So while we're here, I actually wanted to follow up on another. Mike's initial question, I think was correct. I think we just got confused about what geometry he was asking about. And you guys aren't the only ones. I don't mean to call you out for this, but so you guys are using like foam insulation in the walls here, right, to provide the R foam, the thermal resistance of the foam.
Yes.
So the question, I think, and Mike, you tell me if I got this wrong, but I think the question he was asking was like, in your down selection process, why did foam emerge as the winning solution, and specifically compared to just filling that space with nothing, with air?
We wanted to ensure that one temperature control unit wouldn't interfere with the other from our second design review with you, which is why we added the foam.
Yeah. So I'm not asking about cross communication from one container to another. I'm talking about like in the wall itself, right? So I agree that you definitely need insulation in that space to prevent the crosstalk that you just mentioned. But it's and Mike even brought up the Rayleigh number. I don't know if you guys have talked about the Rayleigh number in heat transfer. That's a natural convection phenomenon, which should be covered in an undergrad class, but sometimes is skipped over if the class is rushed. But he was asking about natural convection in that space. And so normally, like if you think about, for example, like a double pane window, right? Double pane windows are used, or triple pane windows are used because they provide a better R value, better insulation compared to just a single pane window that just lets the heat conduct right through. But what's in that space between the panes? It's not foam, it's air, right?
Exactly.
Or it's actually usually some sort of inert gas. And the reason that's done is, one, it's transparent, but two, air typically has a much lower thermal conductivity than basically anything else, right? Any other solid that you can imagine. The whole reason that foam works is because it's mostly made up of air. It's just the issue is if you've got a space that's big enough and you've got a temperature gradient in that space, you can start to set up natural convection currents. That's why Mike, I think, was invoking the Rayleigh number. So I guess ultimately the question is when you guys did your down selection, did you think about, or maybe it sounds like you did this redesign after the down selection process, but was it possible that space could be just filled with air instead of foam, which would save you cost and give you more insulation?
Yeah, it's possible. This was definitely more in the later stages when things were more time crunched.
Okay.
I don't think we had a design in our down selection that even had like that sort of design, so it probably didn't even cross our minds at all.
Yeah.
So,
Well, I don't. Yeah. So I don't mean to, like, I know you guys are like hours from finishing, right? Like I think the FDR is due on Monday, so I don't want to completely have you jump in and redesign the whole thing. But it might be worth in the FDR just looking at, you've already got the space in there already because that's where the foam lives, right? So if you were to take out the foam and just have that inner compartment sitting with an air gap between itself and the outer compartment, can you get away with doing that and not setting up natural convection? And then does that make your resistance in that space, thermal resistance in that space, better? So anyway, something to possibly look at if you've got extra time and brain cycles.
yeah.
Thank
We
you.
would need to ensure that system is completely sealed, right? Because kind of, even if it's just a gap, like if it's not sealed, like the 2-pane windows you're describing, they're not open to the environment. That gas is sealed within the 2 layers, right?
Well, when you say sealed, it doesn't need to be like hermetically vacuum sealed. You probably want to prevent, especially if you're surrounding, you guys aren't controlling the temperature of the surroundings though, right? Like the air.
No.
Yeah. So it probably doesn't matter. In fact, that might be beneficial to have kind of cooler air diffusing into that space, but then it becomes a diffusion time constant, right? So how long would it take air at lower temperature to diffuse down into that space if it's not sealed? And my gut is that's a pretty long time. And the air that's diffusing down into that space is at, I think, in most cases, a lower temperature than your heating system would be at anyway. So that can only help you.
Right.
So yeah, so I don't think it needs to be sealed in like a pressure vessel type way. It just needs to be a chamber within a chamber. So more or less the geometry that you have now, just instead of foam in the space, just air in the space.
Gotcha.
So anyway, something to, and like I said, I didn't mean to harp on you guys because every group has used foam, and I've been sitting here thinking to myself, why is everybody doing this when air is free?
Well, I think, Dr. Traum, if I may, I mean, this is really potentially a curriculum issue, not the students, but it makes me realize perhaps we should have heat transfer as a prereq, or we need to look at that class more closely. But
oh yeah, there you go. We've changed the curriculum.
yeah.
Pioneers, baby.
Okay. So I'm just looking at the time and oh, actually Meg has jumped in and just to let us know that she's on her way out. So thank you for coming by. So we probably should stop there. We do have a 30-minute break built into the schedule. So let me stop recording here.